Hello, in this short video I'm going to solve the following problem for you. In a group G with identity element E, elements A and B satisfy AB squared A inverse equals B cubed and BA squared B inverse equals A cubed. Prove that A is equal to B is equal to E. Pause the video at this point and give it a try. Okay, now we have these two properties and we want to show that the elements involved A and B are both equal to the identity element E. In the proof that I present here, I will use extensively this property that is very well known in group theory. Okay, what is that? If I have two arbitrary group elements and if I have a natural number n, then this combination in which an element is sandwiched between the inverse, an element and its inverse, and I want to raise it to power n, this power n only affects the middle term. It will not affect the terms on the sides. Okay, so this is a very well-known theorem in group theory, and it can be proven very easily using mathematical induction. So I'm not going to prove this property for you, but I will use it a lot in my presentation here. Okay, so the first thing that I will do, I will start with b to the power of 9, and I would write it as b cubed to the power of 3. But now b cubed is given to be ab squared a inverse, so I replace it here, so it becomes ab squared a inverse to the power of 3, and then exactly because of this property I mentioned, this is a group element which is sandwiched between an element and its inverse. I'm supposed to raise it to power 3. A and A inverse will not be affected, but the middle term will be raised to power 3, which gives me A b to the power of 6 A inverse. And I can also write this as a b cubed a inverse to power 2. Why? Because of the same property. This time b cubed is sandwiched between an element and its inverse, and I want to raise it to power 2, so a and a inverse will not be affected, but the middle term will be raised to power 2, which is correct. But now what I will do, again, instead of this b cubed here, I will put ab squared a inverse. Okay, so let us continue here. So I will have a, instead of b cubed, as I said, I write a b squared a inverse. Then after that I have an a inverse, and then I want to raise it to power 2. What happens now? I want to see that this term, whatever it is still sandwiched between an element and its inverse, and I'm raising it to power 2. So this means that this one and this one will not be affected, but this term which is sandwiched between them will be raised to power 2. So I can write it as a b squared a inverse to the power of 2, and then I have a inverse. Okay, but then again, you see how many times I'm using this property. Here b squared is sandwiched between a and a inverse, and I'm raising it to power 2, so a and a inverse will not be affected, but this will be raised to power 2, which becomes, so I have a here, I have a inverse at the end, then the middle term will be a b to the power of 4 a to the power minus 1, a inverse. But now what happens, this a and a becomes a squared, this a minus 1 becomes a minus 2, yes? So then it becomes equal to a to the power of 2, b 4, a to the power of minus 2. So I was able to show that b9 can be written in this way, so let me keep it for the future. So b to the 9 is equal to a to the 2, b to the 4, a to the minus 2. So this is something that I would need. Okay. My goal is now to determine, to find a squared from this relation and find a minus 1 minus to the a to the power of minus 2 from the same relation and put them here. So what I do, I'll start with the given relation b a squared b inverse is equal to a cubed. I multiply both sides from the left by b inverse and from the right by b, so a squared becomes free and it becomes b inverse a cubed b, and of course then it means that a to the power of minus 2 will be the inverse of this expression, but according to the theorem in group theory I can calculate the inverses but in the reversed order, so it becomes b inverse a the power of minus 3 and then b. Yes, so what I will do now, instead of this a squared I put this expression, and instead of this a minus 2 I put this expression, and then of course I will again get b9. Yes, so I would say that b9 is equal to, let me repeat, instead of a squared you put this expression, so it becomes b minus 1 a cubed b, and then you see that you have a b to the power of 4 and then this expression instead of a minus 2 that is here. So this becomes b to the 4 and then b to the power of minus 1, a to the power of minus 3 and b. Yes, so now let us see what I have. This expression here becomes b to the 5 times b to inverse becomes b to the 4 again. So if I continue, it becomes b inverse a cubed b to the power of 4 a to the power of minus 3b. Okay, so this is my b9. Be careful. So b9 is equal to this expression. Now I multiply both sides by b. This b inverse will be cancelled. I multiply both sides from the other side by b inverse. This will be cancelled. I will have a b inverse here. b9, b inverse becomes again b to the 9, but this time this will be left for me. Yes, so it becomes b to the 9 is equal to a cubed b to the 4 a to the power of minus 3. Now if you compare what we had in the beginning and what we have now, because both of these expressions are equal to b9, they have to be equal themselves. So this means that a cubed b to the power of 4 a minus 3 should be equal to a squared b to the 4 a to the power of minus 2. So I can cancel a squared from the left and a to the power of minus 2 from the right. So the left hand side, what is left is a b to the 4 a to the power of minus 1. On the right hand side, what is left for me is just simply b to the 4. Okay, so now let me write b to the 4, and here on the right hand side, so I have b to the 4 is equal to a b to the 4 a to the power of minus 1. Again, using the same relation that I have from the very beginning, I can write it as a b to the power of 2 a to the power of minus 1 to the power of 2. But this expression is again this expression, which is b cubed, so it becomes b cubed to the power of 2, and finally I more or less get what I need because it becomes b to power 6. So we were able to show that the fourth power of b is equal to the sixth power of b, so it means that I can cancel b4 on both sides, then I will get b squared is e. Okay? And then what happens if b squared is e? So A inverse also become E, so B cubed is also E. Okay, so B cubed is E, but B cubed means B squared B is E. I also realize B squared is E, so this means that B is E. Okay, and when B is E, the other one is very simple. Why? Because if B is E, I can use this relation. I can cancel these two because they are just identity element. Then I will get A squared is equal to A cubed. But A squared equals to A cubed by cancellation law. It means that A is also equal to E. Okay, so this is the way I did it. Sometimes because of these abstract problems, you get the feeling that you are making problem a little bit more complicated than it should be. If you think that you can have you can present a better way, I would really appreciate that if you can leave a comment below the video. Anyway, I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.